Alright, in this video we're going to talk about how to create a regression equation from a given set of data. Sometimes this is known as finding the line or the curve of best fit, and it's a very powerful technique that's used in the real world for taking real world data and finding a mathematical equation that fits that data. So we're going to start off, here we are in Desmos. The first thing we need to do is enter our data, and so we're going to do that by coming over here and adding a table of data. Now we'll clear out this old data from here, but we're going to enter our x's and y's, our data that we've gathered, and then we'll work with that. Okay, so I went ahead and entered the data over here, and as I entered those data points, they were plotted here for me. So that's the data, and this is actually data for the x value represents the year starting in 2001, and the y data represents wind power capacity generated by windmills given in megawatts. Okay, but you can see we've got a curve here. We've got this data kind of seems to fit a pattern here. All right, so what we would like to do is we would like to find the best equation, the best curve that fits this data. And we can do that over here by entering in a regression equation. Now, in Desmos, we can do that a couple ways. We can try to fit a linear equation to this data. And if you look at this data, it doesn't necessarily look like it's in a straight line. But let's go ahead and find the best line that fits this data. So we're going to type in the variable y sub 1. Okay, so this is the equation that this is what we want the regression equation to look like, and we want it to be linear. So we're going to use y equals mx plus b, but the only difference is our variables are y1 and x1. So y1, and then we're not going to use equals. The symbol you want to use is this little tilde, which is a shift apostrophe. You'll have to look around on your keyboard to find it, or it's also in the keypad down here under, let's see if we can find it, right in somewhere around here, right there. Okay, so y1, don't use the equal sign, use this little tilde to tell the Desmos that you want to do a regression. M for slope, x1 plus b. And what it does is it finds the line that goes as best as possible through this data. Now, of course, that line's going to miss a lot of those points because those data points are curvilinear rather than linear, right? So it's not going to hit them all, but that's the best possible line we can get through the middle of those. We can see. Now, if you notice the difference between, let's take a point here. This is the actual data point. This is the predicted value on the line. So there's a gap right there. That gap is called the residual. And so you'll see it's that much there. If we go over to this data point, it's about that much. It's smaller. This line is the one line that makes the sum of all those residuals as small as possible. If you want to see those residuals, which is the error between the actual point and the predicted point on the line, click on plot over here, and you'll see that this gives you the error between those two things. Notice right here, the point is practically on the line. So there's very little difference between the actual value and the predicted value. And so that's why our residual down here is close to 0. Ideally, if our line went through all of the points, then all of these blue residual points would be right on the x-axis, indicating that the line goes right through the data. Okay, now we might come back and say, well, maybe a line is not the best curve to go through this data. So let's try a different kind of curve. So maybe not, maybe a line doesn't work well. Let's try one that is one level up in terms of polynomials. So let's try a degree 2 equation, a quadratic. So come over here. I'm going to hide the work I've done with this line just by clicking on that. And let's go ahead and hide the residuals. If I go up to my, let me move this over a little bit. If I go up to my residual table, I can click on that and that will hide the residuals. So what I want to do is I want to do a quadratic curve. See if a quadratic curve fits that data better. Looks like it might have a chance because it looks like it might be a parabola. So what we're going to do is we want to say we want to fit the curve, a curve that looks like this or has this kind of equation. y1, use your tilde, and remember the equation for a quadratic. It's going to be something times x squared, something times x squared, plus something times x. Got to get those ones in there so we're actually dealing with x sub 1, plus c. So ax squared plus bx plus c. And so the Desmos finds the best curve of that form that fits the data. And now look at this. That curve comes a lot closer to those data points than our line, especially up here. You know, it's off right here in the middle a little bit, but even that error or that residual is small compared to what it was. Let's see what the residuals look like. Yeah, see, they're clustered much closer to the x-axis, which tells us this curve does a better job of modeling that data. And what is that curve? If you actually want to know, we should have mentioned this with the line. But if you look back over here, you see that the curve, the purple curve we've graphed is ax squared plus bx plus c. A is 2386.6. B is negative 2869.5. And C is 30,212. Back for the line, we did have a mx plus b as well. And it looks like I may have put in the 5 back there for the line. Let's try that. Yeah, for some reason typed 5 there, but we'll survive, I think. Okay, I could fit other kinds of curves. Real quickly, I could come along and fit maybe a cubic curve to this. Would a cubic curve fit better? Y sub 1 is ax sub 1 cubed plus bx sub 1 squared plus cx sub 1 plus b. Oh, look at that. That cubic curve looks like it's perfect for that data. Look at the residuals for the cubic curve. Right clustered right around there. So it looks to me like if I were going to fit a curve to this data, I would want it to be cubic, and the cubic form, that equation is the coefficients for that equation are given right there. And so that's quite a powerful technique for finding mathematical curves that fit data.